All right. Okay, so let's continue our discussion on determinism. In the last video, I talked about scientific determinism. I provided an argument why I believe scientific determinism is false, and the next stop would be metaphysical determinism, because in scientific determinism basically means predictability, and some people believe that determinism does not really imply predictability. So that's where we get to metaphysical determinism, where we just say that everything are just determined like that. And we will look into arguments why we think that. And most of the arguments, the good ones, are usually related to special relativity. And I will argue, not in this video, but in the next video, why special relativity is actually in favor of indeterminism. So it's just crucial to have at least some essential background on the special relativity itself. So that's what I'm going to do today, give you some background on that, and then the next video I will talk about how we can use special relativity to see the indeterminism, and how we can refute the arguments using special relativity for determinism. Okay, so let's go to our slides, and then I will start with a review of what we talked about in the previous session, and then I will continue to special relativity. All right, so these were the definitions that we were working with. The scientific determinism was the fact that any event can be predicted with any desired degree of precision if you are given a sufficient precise description of past events together with all the laws of nature. So if you can predict based on the past events and current state everything that's going to happen in the future within any desired degree of precision, then that's scientific determinism. And metaphysical determinism says that all events in the world are just fixed, unalterable, or predetermined. Future is as little changeable as is the past. Now, so what was the main problem in scientific determinism? Now you can watch that video, but in that video I prepared like one specific example of showing what kind of events can actually refute scientific determinism. Here I will review it, but in a different way, in a different light, so you can also provide some more information about the exact mechanism of those examples, because that's not a very specific example. You can generate infinite number of them, so it's important to understand what exactly is going on. All right, so in scientific determinism, the assumption is that knowing past events and laws are enough to know everything. But the problem is that systems, whenever we consider systems in our world, it's not just about the state. So systems usually have also inputs. Most of the time, we can even say always have inputs, so they can be influenced. So you have a system, it has a state, it has an input or influences, and then it has an output. But in scientific determinism, we only talk about state, right? We just say, okay, the state of what happened in the past and laws of nature are going to be enough. So the question is, what about the input? What about the input to the system in the future? Well, scientific determinism says, implicitly is assuming that, okay, whatever the input is part of the world. So that should be included in the past events as well. So there's no way out of this. So if I know the past events, then I'm going to know all the inputs to the systems as well, because they are also part of the nature, right? So that's the point. Scientific determinism assumes that the input will also be known once we know the past events. And the problem is that that assumption is false. In classical mechanics, it's also false. In special relativity, it's also false. And as we will see, is actually in special relativity is even the falsehood of this assumption is even more clear. But even in classical mechanics, we can provide examples such as the one that I provided in the previous episode on determinism, that even in classical mechanics, if we are within the system, then this is not possible. So basically, we are assuming that we know all the inputs, but what if the input, or at least part of the input to a system, is something that we just cannot know before the prediction? And that's the prediction results. We don't know the prediction results before we predict it, right? So that's exactly how I created the example of the previous video. So this is what we have. We have a predictor, we have a system. For example, the system is a machine that wants to produce something. And so we look at the states, and what we want to know is the outcome of that state. For example, X, we don't know that. The state will do something, the machine will print something out. And we want to know the X, right? Now, the point is that the system will have some inputs. Now, for us to be able to predict what the machine is going to do, or for example, what a painter is going to draw on a piece of paper, what we need to know all the inputs to that machine or to that painter, right? But the problem is that the prediction that we make, and that's the X hat, that's a prediction that we will make based on the state, based on the past events, will affect or can affect the input of that system. Now, in that example, it was directly affecting it in a sense that you would actually show me your prediction results and I will draw something differently. But it could, in general, it can just have one effect on the system, and that's enough. So we have a very interesting system here, because for us to be able to predict the future of the system, we need to know the input, all the inputs, everything that can influence the system. But one of the things that can influence the system is my prediction of what the system is going to do. So in order to know the input, in order to know all the influences, I need to know what the system would do. But in order to know what the system would do, I need to know all the influences. And that's the problem that we face here. That's the problem of this prediction. To be able to predict, we need to know the input. But to know the input, we need to predict. We need X hat to know the input, but we need to know the input to know the X hat. And that's exactly what's happening in the examples that I explained in the previous video, because if we assume, now this is not possible, if you have two different things and you need to know one thing before the other one, then that cannot happen, right? And if we can have only one system that has an X different from input, for example, a machine that inverts a signal, you give a machine number 5 and it produces number 6. That difference, that's enough to make sure that X and X hat will never be equal to each other. So, so to predict, we need to know the input, but to know the input, we need to predict. So we cannot predict. And if we assume that we make a prediction, we will always be false. For example, if you assume that you can predict that I'm going to draw a right triangle, you show that to me, I falsify your prediction. If you assume that you can predict that the machine will print out number 4, you give that 4, it prints number 5, falsifying your prediction. So that's a problem, right? That we cannot do such prediction because we don't know the input of the future system. So that basically refutes scientific determinism, that it's not possible. It's not possible for us to be able to predict with any desired degree of precision if you're given past events. That's not enough. We cannot do that. So we will go into metaphysical determinism now, but as I said, we need to go into special relativity. All right, so before that, just a couple of terms that sometimes are used for scientific determinism. Sometimes we call this prediction from within, because you can show that anything inside the universe will fail to predict anything. Not anything, but it will fail to satisfy scientific determinism. So as long as we're inside the universe, it's not possible for us to predict future with any desired degree of precision. I will go into some other details of this, because some suggested that, okay, if I'm isolating a system and I'm outside, I'm the scientist doing the prediction, can't I say that, okay, when I do the prediction, I know that I will not interact with the system? And doesn't that imply that then we can actually predict the system with any desired degree of precision? But the problem is no, because remember, prediction from within is impossible. But if you make a prediction about the future, you're also making prediction about yourself. So you will say, okay, I know that I will not do something in the future. But that's again a prediction from within, because you are aware of the prediction results. So just to generate another example on the spot, imagine you're the scientist trying to predict what I'm going to draw, right? You make your predictions, and then in your prediction, you realize that you will not interfere with the system. You will actually do something else. You will be eating some specific food. But upon realizing that information, that, hey, like I'm going to be eating some specific food, you get a reaction out of that. And that reaction affects you. For example, you might have a heart attack and die. And that will falsify your own prediction. You see, so prediction from within is not possible because what we will know about the future can affect us. Now, with the example is me and someone else outside, that's more clear. So there has to be like a communication. But if it's about me, myself, then that's even worse, because you immediately are aware of the prediction results and you're immediately affected by your prediction results, therefore falsifying the prediction. Or maybe just go through it again once more. Imagine you want to know your own future. You want to know what you are doing in 1 hour. Now, to do that, you need to know everything that influences you, correct? But one of the things that will influence you is the prediction results of what you think will happen in the future. But to get those information, you need to know what influences you. So you see, now we get again into that loop. To know what I will do, I need to know what I will do. Before I know something, I need to know something. And that's why we can never know that. So this is not true that the scientists can say, oh, I can predict myself. I'm not going to interfere with the system. You can't. You cannot predict that, because you don't know how the prediction results will influence you. You might see the results and you say, oh my God, if this is the result, I'm going to interfere with the system, and the whole chain again begins. All right, so there's no way out of the prediction from within. Okay, prediction from within, as long as you are inside the universe, is not possible. So some people say, okay, what if we go outside the universe? What if there is some entity or God or demon, something that is not part of the universe? What if then we can say the events are just fixed? Well, of course, we don't have, in that case, we don't have any empirical data, because everything that we do is within the universe, and scientific determinism is not true. So we need some kind of metaphysical argument why metaphysical determinism or prediction from without is true. And that's where special relativity comes in. Okay, so let's get into it. Now, it's best to understand special relativity by comparing it to classical mechanics. So we will use events as, so the main entities that we will be working are events. And I will keep things simple because I don't want to get into the ontology of events. When I say event, just imagine like a flash of light. Okay, so like when I say A, events, it's just like a flash of light of blue. It just comes in, goes out. And B is another flash. We will use events as things that happen at a point in space and a point in time. That's why I want to make everything simple. It's just a light point. It's just in a space and in a point in time, there is a flash. That's it. That's the event. So for example, we have an event B, that's a red dot flash, and A, that's blue dot and blue flash. So those are the things that we will work on. So we have events in space and time, and there are two interesting questions that we need to ask, because we are choosing a point in space and we're choosing a point in time. The question is, what is the temporal difference between A and B, and what's the spatial difference between A and B? Because they're in space and they're also in time. What is the temporal difference between them, and what is the spatial difference? And also for space, I'm just assuming one-dimensional right now, because I mean, you can get into higher dimensions, but let's just assume we have one-dimensional space, just X. So what's the difference between their X? What's the difference between their time? And classical mechanics and special relativity give different answers, and that highlights their difference. What does classical mechanics say? So the first question of these two, that's the temporal difference, has a definite answer in classical mechanics. So what is the temporal difference? The way that we do it is that, okay, you select a unit. You say, okay, the unit is 1 second, or the time for this pendulum to go back and forth. You select a unit, and then you start counting when A happens, and then you stop counting when B happens. You see, A happens, you start your clock, B happens, you stop it, and then you have the temporal difference. And in classical mechanics, this value is independent of the observer. It doesn't matter who is doing that. Everyone will get to the same number. And this means that in classical mechanics, we have a total ordering of events, a total chronological ordering of events. Every event, when you start it, for example, from A, you start counting, it can be positive. If you start from A, you immediately have to stop, and that means that they are simultaneous. Or it might be that the number is negative in the sense that you have to start from B actually counting, and then A, you have to stop it. So if this is a number, this is a fixed number for everyone, this is a universal thing. You can order all events in universe using the value of this clock. You can order all events, and there are only 3 possibilities. Some events, based on each event, some events will be ahead of it, some events will be at the same time, and some will be behind it. So we call this total ordering of events. Again, I insist, total ordering of the events. We call it time. That's where time is coming from in classical mechanics. And based on this total ordering, we can define past, present, and future. Okay, so we get a total ordering. So for example, we have A and B, and then for any other events, we can just put them in an order based on the number of the clock. And based on these ordering, we can define a present. For example, for A, that's the green line. We can have a future, that's the blue part. We can define a past, that's the yellow part. The red part. So the red part is where the clock has to be negative. The green is clock is 0. The blue is clock is positive. So the first question is clear. What about the second question? The second question is more complicated. If A and B have 0 temporal difference, that's the case here that we have. So they are in the exact same time. Then the answer is clear. You just have to select a unit, and then you measure from A to B. And it's again the same for everyone. So we have a clear answer. Any observer, if it's at the same time, you have 2 flashes of light, select a unit like a meter, start measuring. You get the spatial difference. But if A and B have non-zero temporal differences, the 3 cases that I'm showing here, so one of them is after the other one, then the spatial difference can be any number based on the observer. This is what's known as Galilean relativity in classical mechanics. Because in classical mechanics, there's no difference between observers who have constant speed. So basically, based on Galilean relativity, all observers with constant speed, without any acceleration, that is, they're all in rest. So there's no preference of one over the other one. Which means, and since in classical mechanics there's no limit in speed, it means that any 2 events that we can have, they can be at the same place, or it can be different in places based on the observer. And you can realize that, for example, if you imagine that a light flashes in front of you, and then the red light flashes like 1 meter ahead of you, or maybe 10 meters ahead of you. But now imagine that now we say this, but we will modify this. You're moving at a very high speed. So when the A flashes in front of you, the moment that B wants to flash, it's again in front of you. Now the problem is that we cannot really claim that we were moving, because again, all observers with constant speed are at rest. So we can actually say that I was at rest, I was not moving, which would mean that what did I see as an observer? I saw that A flashed in front of me, and sometime later, B flashed in front of me. What is the spatial difference between them? 0. So you see, it changes based on the observer. So that's the relativity that we have in classical mechanics. So the spatial difference can be any number in classical mechanics. So you can see, so A and B can change their places in space based on the observer. That's classical mechanics. What about special relativity? Special relativity, we ask the same questions, but none of them has a definite answer. Let's go into them one by one. Now, for the first question, in special relativity, we can show that there are, for some events, the temporal difference between them can be any positive number, but only positive. Remember that in classical mechanics, this question is settled. There's a definite answer, and from that, we get a total ordering called time. But in special relativity, we don't have that. All we have are these different sets of relations having some specific relations with each other, sets of events having the specific relations with each other. We see that some events, the temporal difference between them can be any number, any positive number, but only positive. It cannot get zero, it cannot become negative. And then we see for some events, the temporal difference can be any negative number, but only negative number, in the sense that they can only be negative, but they cannot become zero. It's impossible to become positive or zero. And we see that for some events, the temporal difference can be any number. It can be positive, it can be zero, it can be negative. So, and I show them with these three cases. So for some, they're always ahead of them. The distance can change in time, but they're always ahead. Some, the distance can change, but they're always behind. And there's some events that the distance can change and it can be in front of you, behind you, or at the same time. So we need to make sure that we understand a couple of things. First, there is no total ordering anymore. Because as we can see, it's not that we can create an order between all events. For those events that the temporal difference can be any number, that we cannot really order them because the order does not exist. So classical time no longer exists. And that's an extremely crucial point. Classical time no longer exists. We do not have a total ordering anymore. However, there is a partial ordering between events. Because as I said, there are some events, so some blue dots with respect to red will always be in front of you. Now the distance might change, but they're always in front of you, and some of them are always behind you. So there is a partial ordering. So some events can be ordered, even though the distance is not constant, but at least the position is correct. So we call that the time-like relation. So we don't have time because it's not a total ordering, but we do have a partial ordering. So we have this thing called time-like relations. Those events that have this specific, so the first and the second one in the bullet points, those events, we will say that they have a time-like relation. It's similar to time because they're always in front of you or always behind you in time, but it's not a total ordering because it's not for all events. So we call them time-like, and if two events are not time-like, we call them space-like. And we will see why we call them space-like when we get to the second question. For the second question, the answer is this. For events with the space-like relations now, distance can be any non-zero number. So now imagine two events that have a space-like relation. The space-like relation would be events that could have any temporal difference. Now, if you are a space-like event, you have two different events, A and B, and they're in a space-like relation, then the distance can be any number, but not zero. And that's where the name is coming from. The space within them is intrinsic to them in the same sense that for time-like, the time ordering between them was intrinsic to them. So the distance could change, but it will always be in front of you in time. Here, if there's a distance, that there's always a distance. Now, the value of the distance might change, but it can never become zero. There's always a distance. That's why we call them space-like. But for events with time-like relation, the distance can be any number. So we immediately see the relation with classical mechanics. All events in classical mechanics are time-like and independent of the observer. There are no space-like events in classical mechanics because as we will see, space-like events are limited, are defined basically because of the limitation of the speed of light. But in classical mechanics, we don't have that speed limitation. So all events are time-like. And because all events are time-like, we just have time. We don't have time-like anymore. It's just time. And the value is also independent of observer. And since we don't have any space-like event, so for the second question, the classical mechanics always gives us the second bullet point. That because they're all time-like, so distance can be any number, as we explained. The second point is that in special relativity, the past, present, and future needs to be redefined because time no longer exists. The time as a total ordering no longer exists, so we need to define past, present, and future in a different way. And since time does not exist anymore, we have a new entity, and that's called a space-time. So we got rid of time. Time does not exist as a total ordering, but now we have this partial ordering that depends also on space, and we have a space-time. Okay, so how do we show all of this? Putting everything together, this is how we look at it. We look at a space-time. Imagine we have all these different events. We have A, B, C, D, and E. First, we define something called the light cone. So the light cone is basically the trajectory of light in space-time from A. So you're moving in space, you're moving in time. If you draw where the light is moving to, then you will get these yellow lines. Now here, I'm assuming that the speed of light is 1, because that's what usually we do in special relativity. The units are changed, so time is 1. But of course, the slope has to be much less because the speed is really high. So you see, as the slope gets smaller and smaller, you're going through larger space in less time. Your speed is increasing. So those two lines, the yellow lines, those are the trajectory of light defining the cone, what we know as the light cone at A. So the blue part plus the red part are called the light cone at A. So that's the cone that we define, right? So what are the timelines? So in a special relativity, we can see all of these different relations between events if we just define the light cone. If we do that, then everything's clear. That's why it's a very useful tool. If you draw the light cone at A, then time-like events relative to A are events falling inside the light cone of A. That's very interesting. So all the events, if you draw the light cone at an event, then all the events that fall into this cone, so inside this part or here, they are time-like to A. And as we say, they are time-like in the sense that there is some kind of ordering in it. And we will use that to define our future, past, and present, because we don't have the total ordering, but we still have the partial ordering. So it makes sense to define all of these concepts based on that partial ordering. So future of A are all the events in the upper blue subset of the cone. So this part, this upper part of the cone, we call it the future. The lower part, the red part, we call it the past. And present would be only A. And that's a very interesting concept in relativity. In special relativity, the present moment only constitutes the event A. And the space-like events relative to A are all the events falling outside the light cone of A. They're neither in past, present, or future because there is no chronological order between them and A. There is no order between C and A. So yeah, that's basically the thing that I wanted to talk about. So that's enough from special relativity. We will use that. We will use the space-time and the light cone to talk about determinism. And we will show that actually using the special relativity structure of space-time, the case becomes much more difficult for determinism. But then how is it that people think that special relativity can actually provide a strong argument for determinism? And that's something that we will see in the next video.